All right, so work done by a constant force is this equation where F is equal to force and D is equal to distance. Force can be thought of as a push or pull. So like if you're pushing, I don't know, let's say you're pushing a block forward, right? Some box or something, or pulling it. So the work done would be your force applying to the object over some distance. So that would be the work or pull. Okay. Let's do a quick example of constant force. Okay. So determine the work done in lifting a 50-pound object 4 feet. So I'm picking it up 4 feet. Okay. You want to know how much work are you doing? So we got the force, right? Equal to 50. We have distance equal to 4. So right now we're using the imperial units, right? So since it's 50 pounds, it's going to be the force of gravity, right? One person. There you go. So basically, if it said 50 newtons, that would be the force in SI units, right? But since they wrote 50 pounds, you should think of that as, oh, okay, that's the gravity on the object, mass times gravity, so therefore it's already in force pounds. I don't like the American units, but oh well, that's what they have in the book. So we'll try this out just so you can see. So right now we are in foot pounds. So work would be equal to force times distance, which would be 200. No, let's show the work. It would be 50 pounds times 4 feet, which would be 200 foot pounds. I hope one day we get rid of these units, but I doubt it anytime soon. 200. I think the last time they tried was the 80s to change to meters. That didn't happen. All right. So this is with a constant force. So you probably saw this in like maybe basic physics, maybe university physics if you've taken those classes. If you haven't, well, it's all right. Basic definition is for a constant force. That's the key word. Is use this. So if you're doing a question on the homework and you notice that it's constant, that's all you got to do. It's multiply. But when does calculus come in, right? Calculus comes in when the force is variable. So work done by a variable force. So meaning the force is changing over the distance. So it's not a constant 50 pounds. Like let's say you're like pushing it. Let's say you're pushing it really fast and you slow down and you speed up and you slow down, right? that'd be a changing force, a variable force. Okay, or if you have a spring, right, and you compress it, depending on where it's compressed, you have different amounts of force. So those are the examples of variable force. So the formula would be derived from this guy up here. It would be from some distance a to b of your f of x force function times dx. This is the variable force formula. Okay. And we got to mention a couple of physics ideas before we start an example here. Let's talk about Hooke's law. So if you're taking some physics, you should remember this. So Hooke's law for springs, right? I'll put it this way. Hooke's law is the force required to compress or stretch a spring. A spring, of course, within its limits, right? Within its elastic limits. Is proportional to the distance proportional to the distance d that the spring compressed or stretched from its original length. So that is F is equal to KD, where where the constant of proportionality K is the spring constant, by the way. Depends on the specific nature of the spring. Okay. All right, so let's move on to an example. Okay, so this is Hooke's law. You'll probably have to find K on these examples because K varies depending on the type of spring. So they'll have to give you probably either the constant, spring constant, and the distance, or the force and the distance in order to solve for K. Okay, so let's do one where we solve for maybe K. Yeah. All right, so example 2. Okay. A force of 750 tons of compressed 750 pounds. Oops, sorry. Compressed is not compressed. A force of 750 pounds compresses a spring 3 inches from its natural length of 15 inches. Find the work done in compressing the spring an additional 3 inches. Okay, so they said the length of the spring is 15. So let's go ahead and draw this crap, right? See what's going on. So they said we have the spring, right, from here to here is 15 inches. Then they compress it, right? Just a little bit. A little prettier. 3 inches. Right, so at that moment, they had 750 pounds of force just to push it from 15 to there, right? So then they asked, all right, well, how much force, how much work done to go 3 more? So they push it even further, right? And they go from here to here, so another 3 inches, right? Okay. So that's the visual. I hope that helps a little bit what we're about to do. So at natural length, so when we're not compressing it, the force is 0, right? If it's at rest and just loose, that's a 0. But when we compress it, that means D, when D is equal to 3 inches, F is equal to 750, right? What they said. 750 pound force. Okay. So if we use our Hooke's law, we should be able to find the K constant, because they said Hooke's law is equal to F, the force of the spring, is equal to some proportional K times the distance. We have the force, we have the D, right? So solve for K. This implies that K is equal to 250, right? So that means our variable function would be 250x. Function. where x is the distance you compress, okay? So this is just Hooke's law being translated into a function, right? This is me applying Hooke's law to find k. So k is 250, so 250 times some x would be the force given some distance x. But since we're changing the distance, it's not one specific distance, we gotta use an integral, right? So to compress an additional 3 inches, this is taking the distance d from 3 to 6, right? Do you agree with that? Because this distance here is 6.
Professor, I'm sorry to stop you here.
Mm-hmm.
I get disconnected for some reason and just came back. So the last thing that I got is F equal KD. The next line, how we get the next line?
Okay, so from here to here?
Yes.
Yeah, so force, so this is Hooke's law right here. This came from...
Yes, I know
right?
that. Yes.
So force is in the question. They said there's a force compressing the spring 3 inches. So when it's compressed 3 inches, I have a force output of 750, or you can think of it as it takes this much to compress. So 750 is equal to k times 3, which is the inches, the distance.
Yes.
So then you can solve for k, which is the Hooke's constant,
yes,
for proportionality, right?
Yeah, got
so
you.
Then you can use this to create your variable function. So this is based off Hooke's law. So the force function will be equal to 250x, where x is your distance of compression. Right. So if you don't compress, right, fx is 0, and I don't compress anything, that would be at 0 force. Right.
Okay.
And if I compress at 3 inches, I should get 750, right?
Yeah.
So you see how the function works?
Yes.
So now we gotta figure out what is the work done. Because force makes sense, but we're solving for work, right? What is the work? So we need to do the integral, right? The integral from a to b of the force function, dx, will be equal to the integral from 3 to 6, because I'm compressing from 3 to 6, the 250x function. Does that make sense? So then when you integrate it, what do you get, right? So add 1 divided by 1 plus 1, 125, right? Now do your values, and you should get 125 times 6 squared minus 125 times 3 squared, which is 3,375 inch-pounds of work. Any questions on what we did?
It's clear.
Now, let me know if it's not clear to somebody here. Now I'm going to move on to another section. So all you're using, one more time, is this formula to find work. Right? This is W. You just need to figure out what is the forcing function, the variable force. Once you have that, it's not too bad. On this note, it's a little tricky figuring out the bounds because they asked for the work for additional 3. So you're starting at 3 and doing 3 more. So that you have to think about, right? Other than that, it's straightforward. All right, I'm gonna move on to a different section then. This next section is a little bit more work. No pun intended there. The center of mass. The 7.5, right? Those scores. Yeah. 1 second.
We're still in the same section, 7.5.
Another section.
The previous one, the work was 7.5.
Oh, that's right. This is 6. So we're going to 6. Oh, I wrote 4 on the last one, right? No.
No, you wrote 5.
Yeah, you put 5.
I don't remember what the heck 4 was. You said it was missing, right, Tomas?
Yeah, 4. We never went over. We did.
Oh, 4 was the arc length.
Yeah. Yeah, it just didn't. It didn't get the notes uploaded. It didn't come out. I got 7.3. You posted that, but the 4 didn't come out on it.
Oh, okay. You say you didn't see the notes. I thought you meant you didn't see the homework.
No, the homework there is the notes. I was looking for the note because I was trying to go back to reference them because I missed some stuff. I was trying to pay attention to it.
Okay, yeah, I'll send it tonight. I thought it was in there. Shoot. Oh yeah, it's part of 7.3. I just didn't label it. So I did label it, it's just not clear. So, but yeah, I'll send it again just to be safe.
Okay. No problem.
It's possible that something went wrong. Okay. This is called moments. Centers of mass. And centroids. Okay. This is the last section for your exam. I don't think we will not be covering 7.7. Okay. So let's start with a simple example, a one-dimensional example. The one-dimensional model for center of mass and moments. Okay. You guys know what I mean by a center of mass?
No.
Yes.
Just real quick. Basically, it's the point that you can balance the object on, like to keep it simple for now. Like, you remember those little birds you can like balance on your finger? You know what I'm talking about? Little plastic birds. Like, all the weight somehow balances perfectly. Or if you have a plate and you put that plate on a small, I don't know, let's say a random stick. And if you can balance the plate perfectly without it falling, you're putting it on the center of mass. So it's like,
Yeah, I understand what you're talking about now.
so that's the center of mass, and it can be found on any object using calculus. So if you have an object that's not, you know, pretty, that's what we've been doing, right? When we have like strange solids, like for example, back in shell washer method, right? We were finding volumes of shapes that were not common shapes. Like if you had a sphere, you would use a sphere formula, right? If it was a cube, you'd use cube. But when the shapes are weird, you have to use calculus to help you out. So same idea here. So find the center of a square would be easy, but if it's not square, then we have to do this. All right, so one-dimensional model for center mass and moments. Excuse me. The center of mass, here's the definition, or the formula, is m equal to the integral from a to b of p of x times d of x, where m is the total mass and p of x is the density function. Okay,
Is the what function? Density?
density.
Oh yeah, okay.
Okay, capital M is equal to this lowercase m right here. So capital M is equal to the integral of a to b of x times p of x dx, where capital M is the first moment okay, keep on going here. X bar is equal to capital M over little m, where X bar is the center of mass. Okay, give me 1 second. All right, so a 30-inch baseball bat rather, can be represented approximately by an object extending from x equals 0 to x equals 30 inches with a density function p of x equal to 1 over 46 plus x over 690 squared. Okay, slugs. All right. So p of x takes into account fact that a baseball bat, or just call it bat, is similar to an elongated cone. So you don't have to figure out the density function in this question. So basically the way they came up with it was
Uh,
assuming the, what's up?
Take into account the food, the what? The food?
Fact.
The fact that what?
Let's rewrite that. The A bat. A bat is similar to an elongated cone. So basically they're saying, well, the bat is kind of like a cone, so they made up this formula. This function. Find the center of mass of the baseball bat. All right. So I'm going to try to show give you as much information as possible since it's the first one, right? So since the bat is 30 inches long, that's where they came up with the object going from 0 to 30. So the integral for little m to find the center of mass, right, is equal to the integral from 0 to 30 of the p of x function. And that's 690 right there. Okay. So they gave you this, and they technically gave you this part, but if I didn't write 0 to 30, you would have to understand that the distance would be or the length would be the bat size, right? So that's all they asked for was the center of mass.
The 1 over 46 is in the law. It have to be 1 over 46, right?
Yeah, that's given to you.
Okay.
This is trying to create the shape of the bat, this function. So
Okay, got you.
the O is derived using a cone and then the density of a cone. So they try to make it this way. But they gave it to us, so we don't have to worry about it. So now at this point, we just need to understand what does this mean and how do you integrate it. So this is going to be just the basic U sub, right? So let U equal to 1 over this garbage plus this thing. Du will be 1 over 690, right? Dx. Which means that 690 du is equal to dx. So there's my side work over here. So m would be equal to the integral from 0 to 30 of u squared times 690 du. So I'm going to put that 690 outside and then integrate u squared, right? So that will give us 690 over 3 u cubed from 0 to 30, but I need to change it back to x. That'll be 6. First of all, can I divide by 3? That number's stuck. I think so. Yeah. That'll be 230 times the original function, 1 over 46 plus x over 690 cubed, right? So plug it in, and you should get about, it's running out of space. Skip the number stuff, right? Little m should be 65 over 1058. Okay, let me double check my stuff here. Okay. So I found little m, correct? That's what this is. But what did they ask me to find? So let me double check this real quick. We go back to the notes. We said little m, where little m is the total mass, and p of x is a density function. I'm sorry. So center mass is just incorporating all this. I misread my own notes here. So now, capital M, where m is the first moment, is this guy. So then you integrate this. Then x bar is the center of mass, which should be this guy. So find little m and big M and then divide them. So we got the first part. So we're not done yet. So this is actually total mass. Okay.
I have a question here. Maybe it's done. But the last step, the 230 multiply the cubic, and then we get the 65 over 1058. The last step, we have to show steps how we get from this to the final answer, or we can put it in the calculator. The one that 230 multiply the cubic root. We don't need to show steps in the last one, right?
I mean,
This, yeah, from here to here. Yes.
No, I mean, you could just plug them in, but don't actually show the pieces.
Yes.
Like I would just put the 30 minus 0 and then just put this.
Right. Yeah, I just want to confirm this.
Yeah, that's fine. Okay. So one moment, please. Okay. So let's find big M. I probably should have made more space, but oh well. So capital M, which we said that is the first moment. All right, so the A to B of x times P of x dx. So in our case, we would be doing the integral from 0 to 30 still, x times a weirdo fraction, or rational function rather, squared. So then now we have to integrate this. So we might need to use some algebra to deal with those ugly numbers, right? Let's see. Yeah, so let's combine those fractions real quick, just so you can see. So multiply this by 15, that will give me 15 plus x over 690 squared. So I combine these two fractions and got this. Let's skip the fraction step. Okay, then I'm going to pull out that 690 because it's in the way. And it's not very pretty, right? Let's see here. Yeah, I'm just going to leave it this way. I'm going to leave it as 1 over 690 squared. It's some big number, right? Who cares? Then you have x times 15 plus x. (15 plus x squared dx). So now it's getting more doable, right? Looks prettier. Then this would be x times, spoil this, that would be what? 225 plus 30x plus x squared. Distribute the x.
We got rid of the square, right?
Oh, yeah, I already squared it. So that'd be 225x plus 30x squared plus x cubed. There we go. So now we can integrate, no problem, right? Just do basic power rules. So this will give us, I'll just put it down here. (225 over 2 x squared plus 30 over 3x cubed plus x fourth over 4 from 0 to 30. And my 690 weirdness is still out here somewhere. Right? So then plug in the 30 in there and see what happens. 690 squared times all this stuff. I don't believe that. 225 times 30 over 2 plus 10 times 30 squared cubed plus 30 to the fourth minus 0. That will give us something. I don't know. This calculator time is. Capital M should be 11,475 over 9,522. So this is capital M. So now we can answer the question, finally. X bar is equal to capital M over little m, which will be approximately these funky numbers, right? 11,475 over 9,522 divided by the little m, which we found to be 65 over 1058. So that is, this is still solid equal. This is the approximate. 19.6 inches. So what you have to do is do an integration. You find little m, do another integration to find big M. The integral shouldn't be that bad. And then you just divide them. Divide what you found. Okay. So this is, yeah. Do you have any questions on this problem? Is it straightforward or is it?
I got a different answer, but I'm just checking my math real quick just to make sure I'm doing it right or wrong.
Okay. Are you off by a little bit or a lot?
Just by a little bit, but I think it's mostly right.
Okay.
Yeah, I think I just did a little error, but it comes up pretty close. The denominator is the same though. I think.
Yeah, I'm sure there's like a small error then. It's fine.
Okay. I just want to make sure. Thank you.
Yeah, but the process makes sense. That's what matters.
Yes, 100%.
Okay. Alrighty. One moment.